Hello student, today we are going to discuss some theorems on limit inferior and limit superior. Okay, so before that, first remark is if sequence Sn where n runs from 1 to infinity is a sequence of real number then limit n tends to infinity, infimum of Sn means limit inferior is less equal limit superior. Okay, limit superior of Sn. Okay, that is if any sequence of real number, then limit infimum is less equal limit inferior is less equal limit superior. Okay, this is a remark of our remark says that limit any sequence of real number has limit inferior must be less equal limit superior. Okay, so then next theorem is if sequence Sn where n runs from 1 to infinity be a sequence of real number and which is convergent. Okay, if Sn be a sequence of real number which is convergent, if any convergent sequence of real number, if sequence Sn be a sequence of real number which is convergent, then limit n tends to infinity, supremum of Sn means limit superior is equal to limit of sequence Sn. Limit superior is equal to limit of sequence. Okay, every convergent sequence of real number we satisfy this condition. If a sequence is convergent, then limit superior is equal to limit of sequence, and similarly limit infimum is equal to, if a given sequence is convergent, then limit infimum of Sn is equal to limit of Sn. Okay, so proof of this theorem. How to prove? Here given that sequence Sn is a convergent sequence. This sequence is convergent, which implies that they has a limit L. Okay, so suppose that, how to prove this theorem? Here given that sequence Sn is a convergent because it has a limit. Given sequence has limit L, which implies that we satisfy Epsilonian definition. By using Epsilonian definition, here mod Sn minus L is less than epsilon whenever n is greater or equal n. Okay, using result, mod x is less than a, which implies that minus a is less than x less than a, means x has value lies in between minus a and a. Here Sn is mod of Sn minus L is less than epsilon. This means that Sn minus L, which is lies in between minus epsilon and epsilon, means minus epsilon is less than Sn minus L. Okay, and this is less than epsilon. So adding L on both sides means L minus epsilon is less than Sn less than L plus epsilon. Okay, and this Sn is a for all n greater or equal n, and then L minus epsilon is must be all terms of Sn are lies in between L minus epsilon and L plus epsilon, and therefore Sn plus 1, Sn plus 2 and up to so on. These all terms are also lies in between L minus epsilon and L minus epsilon. and therefore this is a so their supremum of this Sn plus 1, this all are terms up to so on, this all terms, this is also called as Mn, means Mn is equal to supremum of Sn plus 1. These all terms are lies in between L minus epsilon and L plus epsilon. This means that L minus epsilon Mn is lies in between L plus epsilon and L minus epsilon and L plus epsilon, and therefore mod Mn is must be less than L, subtracting L in both sides we get minus epsilon less than Mn minus L is less than epsilon, and therefore for all n greater equal n, and therefore by definition for this using this definition mod Mn minus L is must be less than epsilon for all n greater equal n, and therefore Mn is any sequence. This sequence has limit L by epsilon n definition. Okay, therefore limit Mn means limit n tends to infinity, Mn is equal to L, and Mn is a supremum of Sn. Okay, limit n tends to infinity, this has also limit L. Okay, so using this is a very simple proof. Okay, so how proof of this our theorem is let sequence Sn be a convergent sequence of real number, be a convergent sequence of real number. Let Sn be a sequence of real numbers which is convergent, that is this sequence is convergent, which implies that it has a limit say L. Okay, it has a limit L, and therefore given sequence has limit L, therefore by epsilon n definition for all epsilon greater than 0 there exists any positive integer set of integer or set of positive integer n belongs to I such that mod Sn minus L is less than epsilon whenever all n for all n greater equal n. Okay, and therefore only rearranging this which implies that minus epsilon is less than Sn minus L less than epsilon by using mod x is less than a, which implies that minus a is less than x less than a. So using this result and adding L on both sides we get L minus epsilon is less than Sn minus L plus L we get 0, only remaining Sn and L plus epsilon. So all terms of Sn are lies in between L minus epsilon and L plus epsilon, therefore L minus epsilon is less than Sn plus 1, Sn plus 2 and up to so on, and this is less than L plus epsilon, and therefore a supremum of any means supremum of this is supremum of this sequence is must be lies in between this set, and therefore here this is Mn or supremum of Sn plus 1 up to so on, this is also lies in between L minus epsilon L plus epsilon, and which implies that L minus epsilon and a supremum of Sn is denoted as Mn. This set Mn is lies in between L minus epsilon and L plus epsilon, which implies that only rearranging minus epsilon is less than Mn minus L less than epsilon for all n greater equal n. Here also n greater equal n, here also n greater equal n. Okay, n greater equal n, right each and therefore by epsilon n definition mod by using this result Mn minus L is must be mod of Mn minus L is less than epsilon, and therefore limit by epsilon n definition Mn has a limit is L for all n greater equal L. Okay, Mn has limit is L, but Mn is therefore Mn has limit L, which implies that n tends to infinity. Supremum of Sn is equal to L. Supremum of Sn is equal to L. And therefore, this is equation number 2. And therefore, from 1 and 2, one is a this equation. Limit Sn tends to infinity. Limit n tends to infinity. Sn sequence Sn has limit L, and limit supremum of Sn has also limit L. Therefore, from 1 and 2, both limits are same. Okay, supremum of Sn is equal to limit n tends to infinity Sn. Okay. Similarly, we show that. Similarly, this is one theorem or remark. Next is if sequence Sn where n runs from 1 to infinity is convergent sequence of real number. Then limit n tends to infinity. Infimum of Sn is equal to, that is limit inferior is equal to limit of sequence. Okay, limit of sequence Sn. Okay, so their proof is similar way. How to prove? Only to change the here. Okay, their proof is same proof as it is, only replace supremum by infimum, and capital Mn replace capital Mn by small mn. Okay, and so write as it is. Okay, write as it is, and here take only replace supremum by infimum. Okay, so similar proof of in this. Their limit n tends to infinity, infimum of Sn is equal to limit n tends to infinity Sn. Okay, then next theorem here take solve in row mode. Okay, similar proof of above theorem, only replacing supremum by infimum. Okay, and capital M by small m. Okay, and all right as it is for this proof of for this remark. Okay, so next theorem is if limit n tends to infinity, infimum of Sn is equal to limit supremum of Sn, that is limit infimum and limit supremum are same, then suppose their limit is also is equal to L. Okay, their limit is L, limit supremum and limit infimum are equal, that is L. Then sequence Sn n runs from 1 to infinity is convergent, and their sequence has limit also L. Okay, here limit infimum and limit suprema are same, then sequence is also convergent and converges to same limit. Okay, their limit inferior converges to same limit L. Okay, both limit infimum Sn, limit supremum Sn has limit is L, then given sequence Sn is convergent and converges to L. Okay, so how to prove this? Here suppose that, okay, limit infimum has L, limit infimum is equal to limit supremum. Okay, and this is L. Okay, that is this sequence is small mn is infimum of this sequence Mn is infimum of Sn plus 1 up to so on. It has a limit L. Similarly, it has limit L, which implies that limit n tends to infinity. Mn has limit L. By using epsilon n definition, by this Mn sequence has limit L, which implies that by epsilon n definition, for all epsilon greater than 0, there exists n1. Okay, here n1 belongs to I, such that mod Mn small mn minus L is less than epsilon. and similarly limit n tends to infinity, supremum of Sn is equal to L. Therefore limit n tends to infinity, capital Mn is equal to L, and therefore this sequence has limit L, which implies that for epsilon definition Mn minus L is less than epsilon whenever n is greater equal n2. Okay, here there exists n2 belongs to set of positive integer I. Okay, so now this is equation number, this one, this two, suppose that. Okay, now then here Mn minus L and Mn minus L, this Mn minus L is must be lies in between minus epsilon and plus epsilon, and this is capital Mn minus L, this is also lies in between minus epsilon plus epsilon. Okay, in this way here taking here this is Mn is equal to infimum of this Mn is equal to infimum of Sn plus 1 up to so on. So rearranging this, L minus epsilon is less than small Mn less than L plus epsilon, which implies that infimum of Mn means all terms of Mn are lies in between L minus epsilon, L plus epsilon. Therefore Mn is infimum of Sn plus up to so on, which is written in the form of L minus epsilon is less than Sn less than L plus epsilon. Because why written in this is because infimum of Mn is a infimum of all this term. Okay, Mn is a infimum of all this term means all terms of Sn plus 1 up to so on, all terms are lies in between L plus epsilon and L minus epsilon. Therefore Sn is one term of given sequence, this n term is also lies in between this L minus epsilon and L plus epsilon. Okay, and therefore L minus epsilon is less than Sn. This is supposed that equation number 1, and for this also L minus epsilon is less than capital Mn is less than L plus epsilon, and therefore Mn is the supremum of Sn plus 1 up to so on, and therefore L minus epsilon is must be less than Sn is less than L plus epsilon, because Sn is one of the term of given sequence. Okay, which implies that Mn must be less than L plus epsilon, and Mn is must be less than epsilon, which implies that Sn is one of the sequence of given Mn is a supreme of Sn plus 1 up to so on, and therefore Mn is less than L plus epsilon, and Mn is supreme of Sn plus up to so on. Therefore all terms of this all terms are must be less than L plus epsilon, and here all terms infimum, all terms are must be greater than L minus epsilon, and therefore L minus epsilon is less than Sn, okay, and which is less than L plus epsilon, and therefore given sequence Sn has limit L. Okay, so this is our proof of this theorem. Okay, how to prove this theorem? Take a firstly given part, let limit n tends to infinity, infimum of Sn is equal to limit n tends to infinity, supremum of Sn, which is equal to L. Okay, and our claim is sequence Sn is convergent and converges to L, that is limit n tends to infinity, Sn has limit is L. Okay, so here given that we are limit n tends to infinity, supremum of Sn is equal to L. Supremum of Sn is equal to L. Okay, which implies that limit n tends to infinity, Mn has limit is L. Okay, supremum of Sn can be written as Mn. Okay, where Mn is supremum of Sn plus 1 up to so on. Okay, and therefore this Mn sequence has limit L by epsilon n definition. For all epsilon greater than 0 there exists n1 belongs to I such that mod Mn minus L is less than epsilon whenever n greater equal n1, and therefore only rearranging minus epsilon is less than Mn minus L is less than epsilon whenever n greater equal n1, and therefore L minus epsilon is less than Mn is less than L plus epsilon. Okay, L plus epsilon for all n greater equal n1, which imply that all terms of Mn are must be less than L plus epsilon. All terms of Mn are must be L plus epsilon, that is Mn is less than L plus epsilon, which implies that supremum of Sn plus 1 up to so on, this is must be less than L plus epsilon. Okay, this is must be less than L plus epsilon, and therefore this Sn is must be less than L plus epsilon, and this is equation number 1. Suppose that this is equation number 1. Okay, also in similar way for infimum also, limit n tends to infinity, infimum of Sn is equal to L, which implies that limit n tends to infinity, small Mn has limit is L by using epsilon n definition. For all epsilon greater than 0 there exists n2 belongs to I such that mod of Mn minus L is less than epsilon whenever n greater equal n2. Okay, and therefore rearranging this minus epsilon is less than Mn minus L is less than epsilon, which implies that L minus epsilon is less than small Mn is less than L plus epsilon whenever n greater equal n2. Okay, and therefore L minus epsilon is less than Mn, small Mn, which implies that all terms of Mn are must be greater than L minus epsilon. All terms of Mn are, Mn is infimum of Sn plus 1, Sn plus 2 up to so on, and therefore L minus epsilon is must be less than Sn for all n greater equal n2. This is equation number 2. Okay, this is equation number 2. Okay, therefore now we choose n is equal to maximum of n1 and n2. If we choosing n is equal to maximum of n1 and n2, then from equation 1 and 2, from this equation and above equation 1, from equation 1 and 2, Sn is less than L plus epsilon whenever n greater equal n, and Sn is must be greater than L minus epsilon whenever n greater equal n. This is equation number 3. This is 4. Therefore from 3 and 4 L minus epsilon is less than Sn is less than L plus epsilon whenever n greater equal n, and therefore minus epsilon is less than Sn plus L is less than epsilon whenever n greater equal n, that is mod Sn minus L is less than epsilon whenever n greater equal n. Therefore by epsilon n definition given sequence Sn has limit L. Okay, therefore limit n tends to infinity, Sn has limit L. This is our proof. Okay, this is very simple proof.